Okay, so we're going to talk about free energy functions today. This is the last topic for this chapter. Okay. So Gibbs and Helmholtz energy, we said, are also known as free energy functions. Gibbs energy is defined as H minus Ts, that's enthalpy minus temperature times entropy, and Helmholtz energy is U minus Ts. Okay. The reason the symbol for Helmholtz energy is A is because it's from the German word for it, which is Arbeit function. Arbeit means work in German. Okay. Now, what's the significance of A? Why did we have to invent more thermodynamic functions? Well, imagine you have a spontaneous process at temperature and at constant temperature and volume, where an amount of heat Q flows between the system and surroundings. Okay, so let's imagine you have a system, constant volume, constant temperature, and a spontaneous, irreversible process happens. Okay, what does that tell you about delta S of the universe? Because the process was spontaneous, when that process occurred, the entropy of the universe must have increased, right? Because that's what the second law tells us. So that's what the second law tells you. Entropy of the universe increases. Now, let's assume that your system and surroundings are at the same temperature and that the amount of heat transfer is small enough so that the temperature of the surroundings does not change. Okay? So we can calculate the delta S for the system. How do we do that? We figure out what the final state of the system is, right? And then we imagine a reversible process that will take you from the initial state to your final state. So that's something we can do. How do you figure out the delta S for the surroundings? Well, imagine that amount of heat that went out irreversibly. Well, think about doing it reversibly. And so if that same amount, okay, is equal to Q surroundings over T, divided by T, that would give you the delta S for your surroundings. But the amount of heat that goes into your surroundings is just the amount of heat that left your system, right? So that's just negative Q of your system. Okay, if you don't specifically state surroundings, you mean the system. So this is negative Q right here at constant temperature and volume. This is for the system. Okay? But the amount of heat that went out of your system is the same as delta U. Why? What do you say delta U was? It's Q plus W, right? But what's W for constant volume? Minus P dV 0, right? So it's just delta U. Okay. So delta S surroundings is minus delta U over T. So we can say then that delta S universe is delta S for the system. This should be delta S, delta U, delta S for the system, right? Plus negative delta U over T. Okay. This is delta S system right here, and that's delta S universe. That has to be greater than 0. So what if that's the case? Well, let's see. Here's what we have right here, the equation. Delta S universe is delta S for the system plus delta S for the surroundings. This is at constant temperature and volume. That has to be positive, right? According to the second law, if the process was spontaneous. Well, let's multiply both sides by negative T. What do you get? Let's look at this equation right here. So negative T delta S, I'm just going to drop the subscripts, okay? Plus negative T times negative delta U over T, okay? That's the left side. What would that be? That's just going to be negative T delta S, negative is positive, and your T cancels out. So that gives you plus delta U, which I rearranged to delta U minus T delta S, right? We can rearrange this to delta U minus T delta S. The left-hand side, if you multiply by negative T, would be delta U minus T delta S. The right-hand side, you multiply 0 by negative T, what do you get? Still 0. Okay, now, since I've multiplied it by negative, what happens to my inequality here? It flips. That is now going to be less than 0. Okay, it's like saying negative 3 is greater than, you can say 3 is greater than 2, right? If you multiply both sides by negative 2, what happens? This becomes negative 6, and that becomes negative 4. So negative 6 is less than negative 4. So if you multiply both sides of your inequality by a negative number, your inequality is flips. So we say then that delta U minus T delta S must be less than or equal to 0. Okay? But at constant temperature and volume, what's delta A? Remember, A is U minus TS, right? So delta A is just delta U minus T delta TS, right? If temperature is constant, that's delta U minus TS final minus TS initial, right? Temperature is the same, final and initial. So that's just delta U minus T, which is the same as T final and the same thing as T initial. And S final minus S initial will just be delta S. So delta U minus T delta S is just delta A if your temperature is constant. Okay? So what this is telling us then, that if you have a spontaneous process, then instead of saying that delta S of the universe is positive, you could also say that if this process happens to be at constant temperature and volume, then delta A must be negative. That means the Helmholtz free energy of your system must have dropped during a spontaneous process. So the significance of this is during a spontaneous process, the Helmholtz energy will be dropping. Okay, so we can rewrite this condition for spontaneity as this equation right here. dA, okay, we're using D instead of delta now, just so we can say that this is for each little step along the way, right? dA would be equal to du minus TdS. That has to be less than 0. So each step along the way during the spontaneous process, your Helmholtz energy will be decreasing. So it's going to be dropping, okay? So when is equilibrium reached? So if this is the progress of your process, right? As your process occurs, what happens to your A? It's going to be dropping. And so dA is going to be negative, right? dA would be the slope of that, right? Versus progress. So what happens when you reach equilibrium then? That's when it reaches a minimum. So if it's dropping, then dA equal to 0, the point where dA becomes equal to 0 is where the derivative, right, would be where you've reached equilibrium. So once it reaches that minimum, okay, what happens when it reaches that minimum? If it goes any further, then it will start to increase, right? So it won't go further. So your equilibrium point would be where it reaches a minimum. Okay? So what's the point of doing this? Well, the nice thing about this is all of these things, du and TdS and A, they're all state functions. They're just properties of the system. Okay? You don't have to worry about what's going on in the surroundings. As long as you know that the process is at constant temperature and volume, you don't have to worry about the entropy of the surroundings. dA will take care of everything implicitly. Okay, so we can just focus on the Helmholtz free energy of your system. All right, similarly, you can make the same arguments for G. Gibbs free energy is H minus Ts, and dG, the condition you'll be able to show is that the Gibbs energy drops as the process occurs during a spontaneous process at constant temperature and pressure instead of temperature and volume. This time we do temperature and pressure. So which one do you think is more important to us in chemistry? The Helmholtz energy or Gibbs energy? Which function have you seen before in freshman chemistry? Gibbs energy. Why? Because we like to deal with temperature and pressure. Pressure is much easier to control than volume. Okay? Because most of the stuff we do is just open to the atmosphere, constant pressure. Okay? So dH minus TdS would be negative. We say that G then, dG equals 0 when you reach equilibrium. So if the process, a small advancement of the process forward or reverse is will not cause a change in G. We say dG equals 0. You have a reversible process. You've reached equilibrium right there. Okay. So G is minimized at equilibrium at constant temperature and pressure. And just like before, we say that the nice thing about this is if you're only dealing with a process at constant temperature and pressure, then you don't have to worry, you don't have to keep thinking about what's going on with the system and the surroundings. You just focus on one particular property of the system, which is the Gibbs energy. Okay? So the question is, why are these things called free energies? Here's the interpretation. Let's say, this is an example right here. Let's say delta U is negative 5 kilojoules. And let's just say T delta S is negative 2 kilojoules. So what would be your delta A? It's delta U, right, which is negative 5 kilojoules, minus T delta S would be negative 2 kilojoules. So that should give you negative 3 kilojoules. So you say your Helmholtz free energy is negative 3 kilojoules. The interpretation of that is this. Well, first of all, since delta U is negative 5, okay, the first law says if this process were to occur, you have to release 5 kilojoules of energy to the surroundings. And how do you release 5 kilojoules to the surroundings? You can do it two ways according to the first law. You can do it by heat or by work. Doesn't matter. Doesn't matter as far as the first law is concerned. As long as you release 5 kilojoules of energy to the surroundings, you're okay. But the second law is what puts a restriction on what kind of energy you have to put out. The second law basically says that the system is free to release up to 3 kilojoules of heat. That's why it's called free energy. So that delta A right there, okay, and remember we're talking about constant temperature and volume here. So that delta A of negative 3 basically says that according to the second law, you're free to release up to 3 kilojoules of heat as work. Not all 5. You can release 5, right? You have to there has to be a net release of 5 according to the first law. But of that, up to 3 can be only up to 3 can be released at work. At least 2 kilojoules must be released as heat. Okay? Why is that? Look at your entropy change for your system. It's negative, right? T delta S is negative. T is always positive, right? So the entropy of your system went down. T delta S is negative 2. To compensate for that, you have to release heat to the surroundings. We say because the process resulted in the entropy of the system going down. So your entropy of your system went down, the entropy of your surroundings has to go up. So you say your system has incurred an entropy debt, and the system has to pay. And the way it pays is it dumps heat. It has to dump some amount of heat to the surroundings to make the entropy of the surroundings go up. Okay? So the heat that is released is used to increase the entropy of the surroundings. Here's another example. Right? Let's say, again, delta U is negative 5, but this time let's say delta S is positive. T delta S is positive 2 kilojoules. So what's our delta U here? Negative 5 kilojoules. Okay, so delta A is delta U minus T delta S. What's our T delta S? Positive 2 kilojoules. That's a total of negative 7 kilojoules. What does this mean? Well, this means that, well, again, the first law says there must be a net release of 5 kilojoules of heat to the surroundings, right? Negative 5 kilojoules is your delta U. What does the second law say? The second law says you can actually dump up to 7 kilojoules as work to the surroundings. Okay, up to 7 kilojoules. Where does the 2 kilojoules come from? It has to come in from the surroundings. So the system can draw, according to the second law, because the system was good, its entropy went up, it's allowed to borrow 2 kilojoules from the surroundings and dump it back out to the surroundings as work. Okay? So 2 kilojoules from the surroundings can be converted to 2 kilojoules of work back to the surroundings. So the net energy change is still going to be negative 5. But as a result of the entropy of the system increasing, it's allowed to do more than just negative 5 kilojoules of work. more than 5 kilojoules of work. Okay? So that's the interpretation of free energy. And so what we've seen basically then is that delta A, if delta A happens to be negative, right, at constant temperature and volume, then we say the process is spontaneous, and the absolute value of that, the magnitude of that, is the maximum amount of energy that the system can release to the surroundings as work. Now, since it's constant volume, what is PV work? 0. So that means this is the amount of work that you can harness to do other things besides pressure volume work. So this is non-pressure volume work. Okay? So like if you have like an electrochemical cell, it could be an electrical work that's done by the system instead of. So this is without pressure volume work. Now similarly, you can show at constant temperature and pressure that your process is spontaneous if delta G is negative, and the absolute value of delta G would be the maximum amount of energy that your system can release to the surroundings as non-pressure volume work. Okay? Because if it's constant temperature and pressure, it has to do some work, right? Minus PdV, volume's not constant, so your work is going to be negative integral of PdV, right? But in addition to that, the amount of non-pressure volume work that the system can do would be equal to the magnitude of delta G. Right? So that's the interpretation of free energy. So we have, again, here's a summary of what we've covered so far. At constant temperature, okay, if pressure is constant, then we say as a process is spontaneous if your Gibbs energy drops. Okay, dG is negative, or we say delta G is negative. This is what we would call an exergonic process. What if dG is positive? What would you call that process? Endergonic. Okay, delta G is positive, it's endergonic. Now, if the process happens to be at constant temperature and volume, then the condition that we look at, if the process is going to be spontaneous, is we look at what happens to the Helmholtz free energy. And what does Helmholtz free energy do at constant temperature and volume? If the process were to be spontaneous, then we know that the Helmholtz free energy is going to be dropping. Okay? Now, there are other criteria that we can use, which is not really common, and because this one would be a case of constant entropy. It's rare for us to be dealing with a process where the entropy is constant. But if entropy happens to be constant, the condition is if S and P are constant, if the pressure is also constant, then delta H must be negative. Okay, you'll have an exothermic reaction. Why should delta H be negative if entropy is constant? So if entropy of the system remains the same, is level, what happens to the entropy of the surroundings? For a spontaneous process, the total entropy must increase, right? Second law of thermodynamics. Okay? So total entropy must increase. If the system's entropy doesn't change, what happens to the entropy of the surroundings? It has to go up. And how do you make the entropy of the surroundings go up? You dump heat to the surroundings, right? And so what is Q at constant pressure, if you remember? Q at constant pressure is just delta H. So it has to be an exothermic process. Negative delta H means heat flows out of your system at constant pressure. So similarly, if the pressure is, if the volume is constant, along with the entropy being constant, then delta U must be negative, right? So if delta U is negative, then what does that mean? You have to dump heat to the surroundings to make the entropy of your surroundings increase. So we say at constant entropy, the processes that are spontaneous are either exothermic, if you do it at constant temperature and pressure, at constant entropy and pressure, or exoergic. Exoergic means delta U is negative. What would be the word for delta U positive? Endoergic. Okay. So spontaneous processes at constant temperature are exergonic, or I don't know, I don't think there's a term for a negative delta A. And for a constant entropy, it's either exothermic if the pressure is constant, and it's exoergic if the volume is constant. All right. Now let's take a closer look now at Gibbs energy, since that's what we're going to be using a lot in chemistry. So dG, if you recall your fundamental equation, right? dG equals negative S dt plus V dP. According to this, what's the partial derivative that's equal to negative S? Me? Here's negative S. Partial of G with respect to T at constant pressure. Okay. So let's sketch G versus T then at constant pressure. Isobar means constant pressure. As a solid is heated and converted into a liquid. What would happen? What is dG dt? If I were to plot G versus pressure, what is derivative of G versus temperature? I'm sorry. If I were to plot G versus temperature, what would it look like? What is dG dt? What do you call that? If I were to plot Y versus X, what is dy dx? That's the slope, right? And what's the slope then of the plot of G versus temperature? dG dt is negative S. Well, S is always a positive number, right? So what's happening so what's the slope going to be? Negative, right? So what's my curve going to look like? It might look like this for a solid, right? It has a negative slope. Okay. What actually happens to the slope? It's not going to be a constant negative slope, but what's actually going to happen to your slope? What happens to the entropy of a solid as you heat it? Anything. You heat something, what happens to its entropy? Entropy increases, right? So what happens to the slope? If the slope is equal to the negative of the entropy, it gets steeper. So your solid might look like that. It gets steeper. The slope gets steeper, right? Now, how does the entropy of a liquid compare to that? So this might be what you would get for a solid. How would the entropy of a liquid compare to a solid? Steeper slope or less steep slope? It's going to be a steeper slope. The entropy of a liquid, it would be higher than the solid. So your liquid might have a curve that looks like this, right? And then your gas would be even steeper. Okay? So that's what the sketch of, so this would be your liquid right here. So from this sketch, can we explain why, in terms of delta G, why freezing is spontaneous below the melting point but not above the melting point? And for that matter, if these curves are referring to the same substance, as a solid turns into a liquid, okay, where on this diagram do we find the melting point? What happens, we say, at the melting point at constant temperature and pressure? There's equal tendency for solid to go into liquid and for liquid to go into solid, right? So delta G in going from solid to liquid would be 0. So that means what? G of the solid is going to be equal to G of the liquid, right? So where is that on the plot? At the intersection. So this point right here, okay, that's your melting point. So this is temperature. Delta G here is 0. Right. What happens below the melting point? What's delta G in going from liquid? Okay, we're talking about freezing, right? So freezing means what? Going from liquid to solid. So if you want to go from liquid to solid, okay, so now I want to go from liquid, which is the black curve, to solid, which is the red curve. What's delta G there? Positive or negative? Does G drop or increase? It drops, so delta G is negative. That's spontaneous, right? Freezing is spontaneous below the melting point. What happens if you are above the melting point? Is freezing spontaneous? You're going from liquid to solid. So here, delta G is going to be positive. Gibbs energy increases. Okay? So that's sort of how you would explain why freezing is favored at low temperature, whereas melting is favored at high temperature. If you think about melting the opposite, then you'll have opposite signs for your delta G, right? Okay. What about G versus T at constant pressure? Okay. G versus, you're still doing G versus T at constant pressure, right? And that was what we talked about last time. Remember we said this was partial of G with respect to T at constant pressure is negative S, right? So how would you determine delta G if for an isobaric heating or cooling from T1 to T2? So Pooh, what's my delta G for to answer this question? What would I write? What would be my limits? From T1 to T2, what am I changing? Temperature. So what derivative goes here? Partial of G with respect to T at constant pressure. Okay? And this is just what? Integral of negative S dt. Here's a way of looking at it. If your pressure is constant, this term just drops off, right? So you can say delta G is just integral of negative S dt. So from T1 to T2. So if I gave you a problem like this on the test, what would you have to do? Let's say I told you a piece of copper from 298 Kelvin to 308 Kelvin. What's delta S? Delta G at constant pressure. What would you have to do? You'd have to look up entropy as a function of temperature, right? So what's entropy as a function of temperature? Okay, let's just use standard values. So let's just do 1 bar pressure. So the entropy at a given temperature would be equal to what? The entropy at 298 Kelvin plus integral of 1 plus the change, which would be integral of Cp dt over T, right? From this is from 298 Kelvin to whatever T you're interested in. Okay. And so that's what you'll have to do. You'll have to look up the expression for Cp as a function of temperature. Where can you find that information? Textbook, or if you want the actual function and literature values, you can go to webbook.nist.gov, right? Let's see if we can find that. I don't know if it's there. Let's see. Oops. Go to NIST webbook formula. Let's just do copper. Space, space reaction. Just collect everything. Okay, here it is. Cp as a function of temperature for your, and your constants that you need are right there. Okay, so you just plug that into your expression, and then you get your, you just do your integral, right? So by doing that, you get S as a function of temperature, and then what do? You just integrate. Now, what if you have experimental data? What would you have to do? What's the integral of negative S dt from T1 to T2? Well, you plot S versus temperature, right? And what do you get? Entropy is going to be increasing. So from T1 to T2, what's the integral of S dt? This is the area under the curve, right? And then you just take the negative of that area under the curve, and you get your delta G. Okay? So what's our delta G going to be if the temperature increases? Positive or negative? Area under the curve is always going to be, S is always positive. Area under this curve is always going to be positive. And so delta G would be the negative of the area under the curve. Okay? Now, what if we just assume that you can, if you're dealing with a narrow enough temperature interval, let's say 298 to 308, within that 10-degree interval, you can say that entropy is more or less constant. How can we simplify this expression? So if your your heat capacity is constant, how do we simplify this? If heat capacity is constant, what can I do with this? Pull it out my integral. That's going to be S naught at 298 plus Cp. What's integral of dt over t? Ln of t. So ln of t over 298, right? So you can say that S as a function of t is entropy at 298, okay, plus Cp ln t minus Cp ln 298, right? So how do you take the integral of S dt? And you're actually going to need to have a negative in front, right? So Catherine, what would I plug in here? I'll put this. I'm putting the negative sign out there. So this is going to be from T1. Okay, we're doing this from 298 to whatever 308, right? For our problem. So what would I have to do here? S naught of 298 plus Cp ln t minus Cp ln 298. Do I have all these numbers? I can look up absolute entropy of copper at 298. What would that be? Oh, that's gas. Is this copper? Gas phase. Oh, so that's gas phase data. I need liquid and solid. Okay. Entropy of the solid down here. Where's the solid? Right here. Okay. So the one I was pointing to earlier was the gas. So heat capacity of the solid down here. Okay, and I can just use the constant value at 298K. S naught is how much? 33.17, right? So that's 33.17 joules per Kelvin per mole. And do I know my Cp at 298 Kelvin? What's my Cp at 298 Kelvin? I have to plug in all of these constants. Oh, that's from 1358 to 1253. Solid phase heat capacity right here. From 298 at 298 Kelvin to 1358 Kelvin, these are your constants that you can plug into your heat capacity expression. Okay? So we're just going to take that as constant from 298 to 308. So you can plug in these numbers for 298 Kelvin and you can get Cp. Or you can just look it up from another source. Let's see, what's another source we can look at. So that will just give us one number. Actually, you can estimate it from the law of Dulong and Petit, right? What's the molar heat capacity of copper? Approximately 3R, right? That is approximate value of the heat capacity, CV, but Cp and Cv are almost the same for copper, so it's approximately 3R. If you just want to estimate, it's 3R per mole. Law of Dulong and Petit, so you can plug in here, this is approximately 3R. So you know your Cp. So all you have to do then, do you know how to integrate ln t dt though? What is the integral of ln t dt? It's not 1 over t. Integral of 1 over t dt is ln of t. So let's see. Let's do that in MathCAD. Integral of dt over t is ln t. But what's the integral of ln t dt? Let's see. Integral of ln of t dt. Okay. It's t times ln t minus t. Okay, so you need to be aware of that one. Okay. So the rest of that is just plug and chug. All right. Let's take a look at the dependence now of g over t versus t. You might be wondering, why are we interested in doing this? We already know how g depends on t. And the reason for that is sometime later we're going to need that to determine how delta g over t changes as temperature changes. Why are we interested in that? Because looking ahead, okay, this is what will give us the link between all of these heat measurements and chemistry. Delta G for a reaction, the standard Gibbs energy of a reaction, divided by T, is in fact related to the equilibrium constant for a reaction. So delta G naught over T is equal to negative R times the natural log of the equilibrium constant. So let's derive the dependence of G over T versus T at constant pressure. Okay, we start off with our fundamental equation, dg equals negative s dt plus v dp. So if I take the differential of g over t, okay, look, g over t is the same thing as g times 1 over t, right? Or 1 over t times g. Let me write it that way. So what do you do when you take a derivative of a product? First times the derivative of the second, plus the second times derivative of the first. So this is the first, 1 over t, times the derivative of g, dg, okay, plus the second, which is g, times the derivative of 1 over t. Well, I'm just using differentials here. You can take the derivative of this with respect to t at constant pressure. So you just divide all of this by dt to get the derivative, right? So, what do we know about dg? It's equal to negative s dt plus v dp. So I substitute negative s dt for dg. Where did the v dp go? At constant pressure, what happens to dp? That drops out, right? So dg is just negative s dt at constant pressure. What's the derivative of 1 over t? It's 1 over t squared dt, right? Negative 1 over t squared. So this is negative 1 over t squared dt. That's the derivative of 1 over t dt. Okay? So that short expression for d of g over t. So we can do the algebra here. What did I do to get to this next step? I have negative s over t, right? And then I have negative g over t squared. I combine all of that. I factored out the dt. What's the next step? How did I get from here to here? What I did was I have minus s over t. I just multiplied that by t over t. Why did I do that? So that I have the same denominator with the other one, right? So that's minus ts. So that's going to be minus ts over t squared minus g over t squared. And so I pull out the negative sign. I just end up with ts plus g over t squared. Okay? But what is ts plus g? What's the definition of g? It's h minus ts. So what's ts plus g? It's just h. So this is just negative h over t squared. Okay, so d of g over t, we say, is just negative h over t squared dt. Or you can say that's also equal to h times d of 1 over t. Right? So this equation right here, if you take the derivative with respect to temperature at constant pressure, okay, then that dt cancels out on the right. This is what's known as the Gibbs-Helmholtz equation. Okay? And if you're looking at a process, then you can also say that the rate of change of the delta G for that process divided by T with respect to temperature would be equal to negative delta H over T squared. So what's the significance of this? You're able to show that delta G over T, the dependence of delta G over T, you can figure out how it depends on temperature by simply looking at delta H. And what do we know about delta H? Delta H is something we can easily measure in the lab, right? So knowledge of delta H would allow us to show how delta G over T depends on temperature. And looking ahead, like I said, knowing delta H will allow us to determine how the equilibrium constant will depend on temperature. And we'll finally be able to explain, give the thermodynamic basis for what you learned in your freshman chemistry as Le Chatelier's principle. Okay? Remember, in your Le Chatelier's principle, you say the temperature increases or decreases, the equilibrium shifts to the left or to the right depending on whether it's endothermic or exothermic. And this is where this is where the connection is, because delta H will give you the algebraic sign of delta H is negative if it's exothermic, it's positive if it's endothermic. So that will allow you to make the prediction as to quantitatively as to whether it's KEQ is going to increase or decrease. Okay. What time do we have? Okay, so what time? Okay. Now dg equals negative sdt plus vdp. Let's look at how G depends on pressure now at constant temperature. So if I want to know how G depends on pressure at constant temperature, what is that equal to? That's going to be equal to the volume. So if I were to ask you to plot G versus pressure at constant temperature, what would it look like? The slope is equal to V. So is the slope going to be positive, negative, or zero? Volume. Can volume be negative or zero? So the volume is going to be positive. So you're going to have a positive slope. So it's going to be sloping upward. What happens when you increase the pressure? What happens to the volume? Goes down. If the volume goes down, so what happens to the slope? It gets less steep, right? So it's steeper at low pressure, and at higher pressure it would be less steep. Okay? Now, if this was for the gas, what would it be for a solid or a liquid? What's the volume of a solid or a liquid compared to a gas? Very small, so it's going to be less steep for a solid or liquid, right? Much less steeper than the and it's almost constant, right? It's much less steeper than the slope for a gas. Okay? So can you calculate delta G then if you were to change, let's say, the pressure on a mole of water, liquid water, from 1 bar to 10 bar? What would you do to this one? You say dg is minus s dt plus v dp, and we're going to assume constant temperature here. So if temperature is constant, what can I drop out from this expression? Catherine, what's my delta G going to be? Integral of what? What am I changing?
Well, the temperature is constant. Could you drop out the negative delta? I mean the negative s dt?
Yes, you drop out the negative s dt.
So
Integral from 1 bar to 10 bar of, and what are we changing? dp, so v dp. Okay, does water change much? The liquid volume change much as you increase the pressure? No. So if volume then is more or less independent of pressure, what can I do with this? Pull it out of my integral, so it's just going to be V delta P, right? V volume times 10 bar minus 1 bar. What's the volume of 1 mole of water? 1 mole of water is 18 grams. What's the density of water approximately? 1 gram per mil. So 18 grams will have a volume approximately 18 mils. 18 mils times 9 bar. What's 18 times 9? 6, huh? 162 times 10 to the negative 3 liter bar. What's a liter bar in joules? 162 times 10 to the negative 3. A liter bar is 100 joules. So that's 162 times 10 to the negative 1. So it's going to be 16.2 joules. Okay? Question? 1 liter atmosphere is 101.325 joules. 1 liter bar is 100 joules. Okay? So that's how you get delta G when you change the pressure of a solid or a liquid. If the volume doesn't change much. Now, if you want to do more precise calculations, what would you have to do? You would actually need to know how the volume depends on pressure, right? So the volume would be the volume, let's say, at 1 bar plus 1. Partial of V with respect to pressure times dP, right, from P naught to whatever pressure you're interested in. What partial derivative, what property of the system would you have to be looking up to get this partial of V with respect to pressure? That's just negative times of V times kappa sub T, right? Kappa, if you remember, is your, this is at constant temperature. Kappa sub T is your, what do you call it? Isothermal compressibility. Right? So you need to look that up, and you can plug that. So now you'll have this as a function of pressure. Okay? Time? Oh. It's 30. And I'm not done with this yet. Okay, looks like I need one more lecture to finish this up.